Hello everyone. Today we will discuss fraud and transaction anomaly classification using Azure Machine Learning. The problem at hand is to implement fraud and transaction anomaly classification model using machine learning algorithms to identify transactions that would fit the profile of a typical fraudulent transaction. Such transactions can be systemically aborted for further research and could be finalized or rejected accordingly. The implementation is done using Azure Machine Learning Studio. Before we get into how we are going to do this, let's quickly get into why are we doing this. Consumers and businesses and financial institutions have been grappling with fraud for decades. With recent advancement in technology, one might expect the trends to reverse. Rather, the conmen seem to have become smarter and have started using cutting edge technologies to conduct fraud. So, could the data trail usually left behind be a means of supplementing a system built to be intelligent enough to look for patterns and flag transactions as fraud? In this project, we will attempt to build one such system using Microsoft Azure Machine Learning. Azure Machine Learning is Microsoft's cloud based ML platform that allows building, deploying, and publishing predictive analytics solutions all from the ease of a web browser. It provides an easy to navigate GUI that enables users to design a simple ML experiment in a matter of minutes. The technology stack that we'll be working with includes EM Editor, GitHub Atom, Anaconda with Python 2.7, packages like NumPy, Pandas, Matplotlib, Seaborn, Tabulate, and Azure Machine Learning. The data that we are going to use has been obtained from Kaggle. It's a transactional data including fraudulent and non-fraudulent transactions and has been simulated by a simulator called PaySim. The actual data for this simulator was provided by a multinational financial organization. Dataset contains over 6.3 million rows and 11 columns and is of size 470 megabytes. Following the machine learning lifecycle, data exploration, cleansing and massaging was performed. We'll quickly go through the notebook and go through the steps that we undertook to perform those tasks. Now we will go through the IPython notebook, look at the code, we will run each of the cells and look at the results as and when they get published. While the code is running, we'll quickly go through the code and see what each of the line is doing. In here, we are reading the file into a pandas data frame. After we read the file, we will be printing the columns and the data types of the file onto the screen. This will help us understand what type of data we have in the file and what data types are we dealing with. Here we could see that we have all of these columns and then the different data types. Next, we will print a few rows from the file that has been loaded into the pandas data frame. We could see that there are over 6.3 million rows in the file that are currently loaded into the data frame. Next, we will see at this function check null NA. The task of this function is to look if there are any null or NA values in the data frame. If there are any values, any of those values, we will get a true as the output from the function. When we pass our data frame through this function, we could see that we get a false, which implies that we do not have any null or NA value in the data frame. Next, we will summarize the different numerical values in our data. We have 5 amount fields. We will summarize each of them and see if data is properly spread out or not. We will also look at different transaction types and we'll see what are the number of transactions each of the transaction types have. So if we look at here, we can see that there is count, mean, standard deviation, minimum, 25%, 50%, 75%, and max values. If we ignore the max values for a moment, we could see that 25, 50, and 75% values are pretty much laid out. Next, we see that there are 5 different type of transactions in the data. We have cash in, cash out, debit, payment, and transfer. Out of these, cash out has the maximum chunk of transactions. Over 2.2 million transactions are cash out, while debit is only 41,432 transactions. Out of all the transactions, 6.35 million records are non-fraud transactions, while fraud transactions are only 8,213 in number. If we take these 8,213 transactions and try to find out what different transaction types exist, we see that only cash out and transfer are the two transaction types that have been performed for fraudulent transactions. There is a column called is flagged fraud. The purpose of this column is to tell if the transaction was flagged fraud by the system. We see that of all the 8,213 transactions, only 16 were flagged as fraud. Now, we'll quickly summarize what we just discussed. So there are 5 types of transactions, out of which cash out has the maximum number of transactions. Data is highly imbalanced. And then the most interesting part is, out of all the different type of transactions, fraudsters for some reason like to choose cash out and transfer as their preferred choice of fraud. There is not even a single transaction other than these 2 types of transactions that were fraudulent. Of all the 8,213 transactions, only 16 were flagged fraud by the system. Now, with this information at hand, we could definitely take out is flagged fraud column, which is pure noise and nothing else. We will also retain only cash out and transfer as the 2 transaction types, and we can ignore the other transaction types for our next set of work. We will perform those transformations over here, and after that we could see that the total number of rows dropped down to 2.7 million in number. Next, we will perform one-hot encoding on the categorical columns, which is type in our case. After we perform the one-hot encoding, we could see that we have all of these columns listed. Next, we will print a few rows from the transform data set just to make sure that everything looks good. We will also look at different amounts that are being transacted and see that if the amount that has been transacted reflects correctly in the new destination balance and is also debited from the origination account balance. There are a lot of cases where we see that that's not true, and especially in the fraudulent transactions case. So we will create 2 new columns called destination mismatch and origination mismatch, which would represent if there is a mismatch between the amount transacted and the balance that was supposed to reflect the amount that was transacted. If there is a mismatch, we will mark the column as 1. If not, we will make it as 0. After making that transformation, we could see that we have these set of columns in the new data set. We will transform this data set into a CSV file so that we could run our models on top of it. Next, we will quickly create a heat map to see that if any of these columns or any of these features are correlated with each other. We will run them separately for fraudulent transactions and non-fraudulent transactions. When we look at the heat maps, we could see that there are no features that are strongly correlated to each other. In case of non-fraudulent transactions, and even in the case of fraudulent transactions, type cash out and type transfer are negatively correlated, which is kind of intuitive. Next, we will look at the balance transfers, the destination balance after transaction and source balance before transaction. Most of the data which we see is kind of concentrated in this between 0 and 1 on the x-axis, which tells us that the amounts that have been the transaction amounts are relatively small in case of fraudulent transactions. Next, we will look at if fraudsters prefer a certain time or day of the month to make the fraudulent transactions. If that could be proved, that could be a interesting thing to look at. When we print the scatter plot, we could see that here the data is pretty well more randomly spread out, and hence there is no clear-cut pattern over here, and hence we can say that the fraudsters do not like to make any fraud activities on a certain time or day of the month. Next, we will be plotting the scatter matrix of all the features in our new data set. Now, quickly we will move on to the Azure Machine Learning Studio, and we'll create a fresh experiment and we'll run it. To do that, we will open a new browser and we'll type studio.azureml.net. Since I'm already logged in, it shows me my experiments. If you will have to log in, you would click here and you will choose sign in option. I'll click on my experiments and it'll take me to my dashboard where I could see all my different experiments. Let's look how we will create a new experiment. So this is the dashboard I was talking about. Now we will click new over here. There are multiple options to choose what type of experiment we want to create. We will quickly start with a blank experiment and we'll build as we proceed. Once we click on the blank experiment, it opens a template like this. We do not want to have an experiment with a name as shown above. We could name it to something else. Let's name it something more interesting. Since our data is, I have already uploaded the data as part of my project, I'm going to take that data set and drag and drop it over here. You can drop it anywhere on this workboard. Next, we will select the type of columns we want to bring into the experiment. We'll go to manipulation, pick up select columns in the data set, and then we will link these two together. I'll launch the column selector and pick all the columns other than column 0. Column 0 is nothing but the index of the data frame. When we exported the data frame into CSV file, it created a brand new column called column 0 to represent the index. We certainly don't want to include it in our experiment. Next, we will split the data into test and train. We'll take the input of this, pass it on to here, and then we will say 50% is train and 50% is test. I'm not going to change this. We have ample of data, and I feel comfortable taking 50% of it for training and leave 50% for test. Next, we will look at the choice of models that we want to run. We'll go to initialize model, choose the category as classification, and then we will choose two class boosted decision tree. There are multiple options to choose from, and for the purpose of benchmarking my two class boosted decision tree, I'm going to choose two class base point machine. Next, we will go to train model and pick up the train model module and drop it over here. This module will take two class boosted decision tree as input and will take the train dataset from here. Similarly, we'll drop a train model for our two class base point machine. In both the cases, the train model needs to know what is the label that it should try to train. Look at the column selector. In our case, it's is fraud because we are trying to find out if a transaction is fraudulent or not. Once we do that, the red icon over there, which symbolizes error, will vanish. Next, we would want to also see if we have to do any scoring. So for scoring purposes, we'll pull score model out of the score section and we'll pull another one for our benchmark model. Score model will take input from train model and will take the test output from here. I need to make a small correction. I have to take pass train onto the model. Yes. Next, we'll take this and pass it on to score model for two class base point machine. We would also want to see feature importance that our model chose while trying to learn. So we'll drop a feature permutation feature importance module over here. Similarly, we'll do the same for our two class base point machine. We'll drop the train model input and drop it here. This feature importance would take data from our actual data set. We'll make the connection from there. Similarly, we'll take it from this model, drop it here, and from the source data set over here. Finally, we would want to evaluate our both the models. There are multiple ways of doing it. We could cross-validate our models for better performance, or we could simply evaluate them. So to do that, we will be looking at machine learning section, look at evaluate, pick evaluate model. We'll drop it right over here. We'll pass on the input of score model from one of the models and the other one from the second benchmark model. Before we proceed, we would want to tune our two class boosted decision tree. While performing the tuning of the parameters, I found out that the best accuracy or the highest accuracy I was able to get was on if I was having 25 as the maximum number of leaves in each tree. Number of samples were 10, learning rate was 0.1, and number of trees constructed were 100. These parameters, I'm going to now run the model. To run this experiment, we'll just click run over here, and it'll transition for running into a next slide. Now we will wait for the experiment to finish. Finally, our model is complete. It ran for approximately 8 to 9 minutes. We will quickly look at the results in evaluate model module. We'll click on evaluation results, click on visualize. Here we will see that the results of ROC curve. We could see that both the models, the red one is our two class base point machine and the blue one is our two class boosted decision tree, which is our primary model. Both of them perform very well as far as the ROC is concerned. The true positive rate to false positive rate came out good. Area under the curve is pretty good for both of them. Next, we will look at the precision and recall curve. This is where the things get interesting. The precision and recall curve tells us about the precision and recall of any given model. In cases where the data is highly imbalanced, the precision and recall would show a trend something like this if the model did not perform well, which happened in the case of our uh, the benchmark model. However, our model, the primary model, which was the two class boosted decision tree, performed very well, and we could see that area under the curve came out to be really good. If you look at the parameters below, precision is 0.998 and accuracy is 1. Recall is 0.996 and F1 score is 0.997. The area under the curve is 0.998 and with a threshold of 0.5. One of the important things to consider over here is that since we are finding or we are doing fraudulent transaction classification, the cost of a false negative is very high compared to the cost of false positive. What I mean by that is cases where a transaction is fraudulent but the classifier identifies them as non-fraudulent, the cost is very high because in that case we are actually losing the money to a fraudster. Cases where a transaction is non-fraudulent but the classifier identifies it as fraudulent are still okay, even though there is an additional step to confirm whether the transaction is fraudulent or not. But that is still that has less cost associated to it compared to the earlier case. In our example, in our case, the both false negative and false positive are pretty low, which implies that our model has performed really good. Next, we will look at the feature importance for our primary classifier. If we look at it, the primary classifier relied heavily on origination mismatch, which was the column we added. Next, it took new balance at origination. Next was old balance destination, and old balance origination was pretty low. After looking at feature importance and comparing the results of our evaluate model, we will quickly go back and look at the lessons learned, pros and cons. Azure ML is a powerful platform to perform machine learning experiments. The interface created by Microsoft intends to enable data scientists to concentrate on essential steps of developing machine learning experiments and analyzing outputs rather than digging too much into the coding aspect. One of the biggest advantages of Azure Machine Learning is hosting the experiments on the cloud. This is very important, especially while working on ML, which most of the times requires machines hardware to be of very heavy configuration to run the experiments. However, Azure ML makes it redundant by allowing the entire experiment implementation to happen on the cloud. Further, the successful experiments can be converted into a web service, which gives an interface to run the model on data to obtain the predicted outputs. The integration of the platform with R is seamless and is a big plus to allow users to migrate their existing set of models developed and implemented locally or another platform using R. While Azure ML has been impressive throughout the experiment and project phase, one of the items that I did not find very appealing is the lack of complete Python integration. To conclude, financial fraud is a menace and impacts both businesses and consumers. Therefore, it is essential to continuously work on new mechanisms or techniques that would thwart the attempts made by the fraudsters. Since there is plenty of transactional data available, it could provide some interesting insights into the fraudulent transactions characteristics. Using this idea, we have demonstrated a very reliable classifier that could flag the fraudulent transactions. Such a classifier could then be translated into a web service and added as a layer between all transactions that happen across the institutions. Any transaction that is flagged by the classifier as fraudulent could then be routed for further scrutiny. We use Azure ML as our tool for this project. It provided a robust, efficient, and fast platform to explore and build experiments. While it has a very good integration with R, a better Python integration would make it a hard to beat platform for ML implementation. To conclude, We have successfully demonstrated building a fraud and transaction anomaly classification mechanism using Azure ML. Next steps. Now that we have created a classifier for detecting fraudulent transactions, next we could implement the classifier using neural networks and evaluate the performance compared to the traditional models. With this, I have concluded my presentation. I hope you enjoyed it. Thanks for listening and have a good rest of your day.